Alright, let's get started with Lesson 11, Size of Atoms and Ions. Now, in this lesson, we are going to apply Coulomb's law and effective nuclear charge to the size of atoms. Now, the size of an atom is known as the atomic radii. The atomic radii, by definition, is the atomic radius is half the distance between two nuclei in a sample of an element. So for instance, we have a diagram here, and we have two atoms that are hydrogen. And in the center of these atoms is, of course, the nucleus. Alright? And we can't really measure the distance from the nucleus to the outer electron shell directly. So what we do is we have two atoms that are close together or bonded together, and what we can do is measure the distance between those two nucleuses. And then what we do is we cut that distance in half, and we call the half the distance then is the atomic radius of that element. And so it's kind of a rough estimation of the size, but this method is very effective and does a pretty good job. Right? So essentially what we need to look at now that we understand what atomic radii is, we need to look at what affects the size of these atoms. What makes one atom bigger than another by its atomic radii? What are the influences of those? And the bottom line that comes down to is Coulomb's law, really. And we need to apply Coulomb's law with effective nuclear charge here with this idea of atomic radii size. So I have a graph here, and this graph is looking at the atomic radii for the first 36 elements on the periodic table. So on the y-axis we have the atomic radii in picometers, and on the x-axis is the atomic number. So each plotted point here gives us the size at a particular element. So for instance, right here, this one, that element is hydrogen with an atomic number of 1, and that is helium with an atomic number of 2, and this represents the size, the radius size of lithium, and so forth. Okay, so you kind of get the idea. So what you might want to do is take a moment and look at this graph and get familiar with it. So you can pause this recording. This graph is pretty important for the test, and the trends and the patterns that you're going to see in this graph, you need to be able to interpret and to analyze it. You should be able to take one atom and compare it to another atom's atomic radius and be able to explain why that atomic radius is the size that it is, all right, compared to the other atom. So first of all, let's talk about what we're seeing here overall in our patterns. You should notice that when we're moving across a period. So let's take period 2, okay? Period 2 starts with lithium, and it ends with neon, okay? Now, you'll notice that as we're moving across the period from lithium to neon, period 2, the size of the radius is getting smaller, all right? Why is it getting smaller? Why does the radius get smaller as we're moving across a period? And you'll see that with each of the periods. Here's period 3, and you'll see as we go across period 3, the radius is getting smaller. As we go across period 4, in general, the radius is getting smaller as we're moving across periods. Why is this the case? Well, let's take a look at this in terms of Coulomb's law and effective nuclear charge. If you look at your periodic tables, and you will notice that the atomic number increases going from left to right. So within period 2, lithium has an atomic number of 3, and neon, the last element in that period 2, has an atomic number of 10. So if the atomic number represents the number of protons, then it tells us that as we're moving across the periodic table, the nuclear charge is also increasing from 3 to 10. And because the nuclear charge is increasing, it also tells us that the effective nuclear charge must be increasing. And since the effective nuclear charge is increasing, that means the magnitude of the force from the nucleus of the atom that to the valence shell is getting stronger as we're moving across the periodic table left to right. All right? So if, based on Coulomb's law, meaning that when the magnitude of the charge increases, there's going to be a greater force of attraction. So you can look at it in terms, I think, that the easiest way to understand the size of the radius. The size is getting smaller because the magnitude of charge in the nucleus is getting larger. Therefore, the magnitude of force between the nucleus and the valence electrons are getting stronger, and this is going to create a very strong force between the nucleus and the valence shell, and the atom begins to shrink. It gets smaller. All right? So just like it states down here, the atomic radius gets smaller as you move across the periodic table left to right. This trend is a result of the nuclear increase in nuclear charge as you move across the periodic table left to right. The added electrons in the same shell, so the distance between the nucleus and the valence electrons does not change. So in other words, we're saying that as we're moving across the periodic table, distance between the nucleus and the valence electrons is not going to have an effect on the attraction because the distance isn't going to change. The only thing that's changing is the number of protons in the nucleus. All right, and so the magnitude charge increases, therefore the attraction between the nucleus and the electrons, valence electrons, is going to increase. Coulomb's law states that when the nuclear charge increases, the attraction between the nucleus and the electrons also increases when the distance is constant. Okay? So that really explains then the radius of these atoms as we move across a period in the periodic table. It all deals with magnitude of charge in the nucleus. All right? So what about within a group? What do we see? What kind of periodic trend do we see occur as we move down a group? Okay, so let's take a look at our graph again. So within a group, let's take, for instance, let's look at group 1. Okay, so group 1, we start out with hydrogen right here, and then lithium, where it'd be right there, and this would be sodium, and this would be potassium. So what do we notice? General trend is that the radius is getting larger as we are moving down a group in the periodic table within a group. So in other words, hydrogen has a smaller radius than lithium. Lithium has a smaller radius than sodium. Sodium has a smaller radius than potassium. Potassium a smaller radius than rubidium, as we can see in group 1. So why is the radius then increasing as we move down a group in the periodic table? Okay, why is it happening? Well, you'll notice that there is, from group to group, there's a large jump here in size. Okay? And what could that large jump represent? Well, it turns out that this large jump that we see, that I am putting these arrows to, represents a change from moving from one shell to the next. So when we go this last element, which is helium, and then we go to lithium, we're actually changing shells. And of course, when we're changing shells, these electrons are getting further from the nucleus. So what we're seeing here is that as we move down a group, the size is increasing because we're adding more electron shells. And therefore, the valence electrons are at a further distance from the nucleus. All right? And so we're going to see this in the statement here. The atomic radii trend within a group is based on the distance the valence electrons are from the nucleus. Going down a group, a new valence shell is added, increasing the distance the valence electrons are from the nucleus. This results in an increase in the size of the atom. All right? So, there are two things, or two schools of thought that we got to look at here. Distance and magnitude. It appears then that the magnitude is more important. So the magnitude on the nucleus, the number of protons, is more important as we move across a period than it is down. Down a group is based on the distance using Coulomb's law, and within a period going from left to right, it's all about the magnitude of the nuclear charge. So to summarize all of this, then, the atomic radius gets smaller as you move across the period, or the periodic table, left to right. This trend is a result of the increase in nuclear charge as you move across the periodic table, left to right. Whereas going down a group, in a group setting here, is going down a group, a new valence shell is added, increasing the distance the valence electrons are from the nucleus. This results in an increase in the size of the atom. So again, as we see a period, what's happening, the trend that's happening within a period is influenced by the increase in nuclear charge, and the pattern or the organization that we see with size of an atom within a group is based on the distance. And so you need to put those two together, and you're going to begin to understand how the periodic table works and understanding properties of elements. So the radius increases going from left to right because the magnitude of charge increases. So in other words, the number of protons increases, whereas the in the periodic table, going down a group, the size gets bigger. Okay, so we get bigger going down, and that's solely because, and that arrow is wrong, and it's solely because there's an increase in distance. So there it is in a nutshell. You really need to come to terms with this and make sense of this. So if you need to look at this lecture video multiple times, do so. Really ponder, think about these concepts, and if you can understand this, understand how distance affects groups and increase in nuclear charge affects the period, you'll begin to understand other properties that we're going to look at later on here in this unit and in other units in the future. All right? So this is it for now for this lecture video. Study hard and be prepared for the quiz. That's all for now.